When I think of Democritus, I like to picture this wizened old bald guy standing with his even more wizened teacher, Leucippus, at the top of a cliff overlooking a sandy beach far below. I imagine them having a lively discussion about how the beach looked like one continuous ribbon of sand. When you step closer, however, you can see that, in fact, it is composed of individual particles of sand, which are discrete unto themselves. The sand is not a continuous stream of matter. Likewise, isn't it probable that all matter is like this? The water in your glass may look continuous as it fills up the glass, but perhaps we just can't get close enough to see the individual particles. If we were able to zoom in on that water, we might be able to see the particles that make it up. Leucippus and Democritus called these smallest particles atomos, meaning indivisible. Since the time of the Greek philosophers, we have learned much about these particles, despite the fact that we've not been able to actually see them. It's important to note that as we learn more about the atom, the best that we can do, for the most part, is to construct models that represent our understanding. I don't mean like model airplanes or cars, but conceptual models, ways of picturing the atom. It is because we are not able to see the inner workings of the atom that we rely on these constructs. Even if we can only represent our current version of understanding, it gives us a framework to hang our new observations on and test our theories against. Okay, so back to our Greeks. These guys were not scientists, but philosophers. They did not experiment to test their ideas and therefore could not prove or disprove their theories of atoms. This was back around 400 BC, and over the 2,000 years that followed, the labs were the domain of alchemists. Alchemists were practitioners who mixed science with mysticism and who obsessed about changing metals into gold. Even though these guys were not well known for their science, there were some elements discovered during this time, as well as processes of metallurgy, tanning, gunpowder, ceramics, and other industries of the time. The term chemistry was coined by Robert Boyle in the mid-1600s when he began to perform careful quantitative experiments. Boyle made significant contributions to our understanding of the behavior of gases. Despite his careful work with gases, Boyle was still an alchemist and clung to the idea that metals were not basic elements and could be converted into gold. Sounds kooky, right? By the late 1700s, one area that had been studied in detail was combustion. After all, everyone likes a good fire, right? In the earlier days, the idea about fires were that they gave off a substance called phlogiston. And when the air around a flame became saturated with this phlogiston, the flame would go out. When oxygen was discovered to support burning, it was called dephlogisticated air, which, admitted, is a pretty cool name. In the late 1700s, a French scientist named Antoine Lavoisier finally explained how oxygen, which he named oxygen, not dephlogisticated air, was needed for combustion. Lavoisier was, like Boyle, very careful about his measurements and is able to quantitatively demonstrate one of the key ideas of chemistry, the law of conservation. Okay, so let's look at how this might be done. If we take a candle and place it in a closed, sealed bell jar, let's measure the mass of the candle and the jar and all. We'll light the candle by using some phosphorus and hot metal and watch what happens. Clearly, some chemical change has occurred. There's soot and moisture on the jar. The candle seems to have gotten smaller, or at least the wick. Where was all that stuff? It had to be inside the candle and the air. Somehow, the matter rearranged itself to create new substances. What's more, when we measure the mass of the system with the new stuff in it, it remains unchanged. Whoa! Mass is conserved. This is a vital principle we'll make use of when writing our chemical equations and calculating our stoichiometric problems. All right, more on that stuff later. If we performed similar experiments and made careful measurements, we might be able to see the ways these materials combined or broke down. It was another Frenchman, Joseph Proust, that was able to show that compounds always had the same proportion of elements by mass. This has come to be called the law of definite proportions. John Dalton, an English schoolteacher, took this a step further and noticed that if an element combined with another element in several ways, making different compounds, the ratio of the masses compared with each other was always a whole number multiple. Okay, that's confusing. Let's look at an example. Let's say that oxygen combines with nitrogen in a variety of ways. In one compound, the ratio of nitrogen's mass to oxygen's is 1 to 1.75. In another, it's 1 to 0.875. And in a third, it's 1 to 0.4375. If we compare the oxygen in each compound, we see that the 1.75 to 8.75 to 0.4375 ratio is really a 4 to 2 to 1 ratio. They are whole number multiples of each other. Dalton published his atomic theory in 1808 with the following postulates. First, each element can be divided into individual particles called atoms. Second, all atoms of the same element are identical and different elements are different. In other words, all atoms of hydrogen are identical to each other, but they are different from atoms of oxygen. Third, all compounds are produced from a set proportion of atoms of each element. Fourth, chemical reactions simply change the way the atoms are connected and arranged, but matter itself is conserved.